We are looking at section 7.3, and it's the introduction of logarithmic functions. And we want to remember what we talked about in class, that logarithmic functions were created so that we can now solve for variables that are in the exponent. And we found that logarithmic functions were inverses of exponential functions. So we started off with the idea of a logarithm, and a logarithm is a function that is created by this definition. So for any b that is greater than 0 such that b does not equal 1, log base b of x equals y, if and only if b to the y equals x. So that relationship must hold. And that's how we define logarithms. So what I want you to get from this definition is that we can switch back and forth between what is called log form and exponential form. And by switching back and forth, sometimes in solving equations, it allows us to solve for variables that before today we wouldn't have been able to solve for. So when you see something like log y equals log base 3 of 9, which is the way we would read this, log base 3 of 9, that is the logarithmic form. And if we were asked to change that to exponential form, well, the base of the log is also the base of the exponential. So if it's log base 3, then we have 3 as the base of our exponent. And I always say that logarithms are exponent-finding functions. So when you perform a log, you are finding an exponent. So that means 3 is the base. That means y must be the exponent. And then the number that's left is what we set this equal to. So we have 3 to the y equals 9. That is called the exponential form. So given that, by changing the look of this expression, changing to exponential form, we would be able to solve this. 3 to the y equals 9, well, that must mean that y equals 2, because 3 squared is 9. So that also means that log base 3 of 9 equals 2, because we just solved for that y. So in the homework tonight, you will be switching back and forth between log form and exponential form. Okay, so let's practice this a little bit, going back and forth between log and exponential forms. So they've given us what is the logarithmic form for each equation, and the one they've given us is 100 equals 10 to the second. So again, the base of the exponent is the same base that we use for the log, so the base is 10. 2 in this equation is the exponent, and I'll just call the 100 the answer. We're going to rearrange these to put it in log form. So the base of the exponent is also the base of the log. So we would have log base 10. Logs are exponent-finding functions. So the log, when we set up our equation, is equal to the exponent. So the exponent was 2. And the value that's left goes in this blank, and we called that the answer, so we'll just say that's the answer over here. And so we will have 100 here. So log base 10 of 100 equals 2 is the log form of the equation 10 squared equals 100. And just as a side note, when we see log base 10, it is called the common log, and it is the only log that you may see written without any subscript. So if you see log without a base written here, it is talking about log base 10. There is another one that we don't write a subscript for, but it's written differently, and we'll talk about it a little bit later. It's called the natural log, and we'll cover that in a later section. But right now, when you see log written without any subscript, that means log base 10. All right, so now that we have this new function, we're going to be shifting, stretching, and reflecting it just like we have been with all of our functions throughout the year. So if there is a coefficient out in front, that letter A that we use for our stretch factor, as always, if the absolute value of A is greater than 1, it's a vertical stretch. If the absolute value is between 0 and 1, it is a vertical compression. And if A is less than 0, meaning we have a negative out in front, then it is a reflection over the x-axis. Horizontal translations, remember those are shifts, are inside the function here, just like they usually are. And again, when it is inside the function, it does opposite of what you would expect. So if it says -2, it goes right 2. And if it says +2, then it goes left 2. And then the vertical shift is the value out here, the +k. And this one does exactly what you would expect. So if it says +5, it goes up 5. And if it says -5, it would go down 5. And then if it has all of these transformations together, there's our stretch, here is our horizontal shift, and here is our vertical shift. So you will be identifying some transformations in the homework tonight, just like we've been doing in all of our chapters. Okay, so I said earlier that log functions and exponential functions are inverses of each other, and I wanted to illustrate that with a graph. So the red graph is y equals 2 to the x. That shows exponential growth. And here is our reflection line for inverses, which is y equals x. And here is log base 2 of x. So this is our second equation, or sorry, our third equation, really. Y equals log base 2 of x. Please notice if I fold on that line y equals x, the red graph and the green graph would overlap each other, showing that they are inverses of each other. They are reflections over the line y equals x. All right, and one of the homework problems deals with the Richter scale that is used for earthquakes. The Richter scale is a logarithmic scale, and now that we're playing with logs a little bit, we have a method where we can compare how much bigger an earthquake of magnitude 7.9 is to an earthquake of magnitude 6.9. So, and the way we do this is we want to, this is the intensity of the first earthquake over the intensity of the second earthquake. And over here, the m is the magnitude of the first earthquake and the magnitude of the second earthquake. Probably easiest always to put the bigger intensity on the top. And by isolating I sub 1 over I sub 2, that's going to be our comparison of the two earthquakes. So if we can isolate I sub 1 over I sub 2, then we can see how many times bigger the first earthquake is to the second. So let's fill in what we know. We have log of I sub 1 over I sub 2 equals the magnitude of the first earthquake was 7.9, and the magnitude of the second earthquake was 6.9. 7.9 minus 6.9 is 1. And notice that this log is written without a subscript, so that means it is log base 10. And I'll put that in here just to remind ourselves of I sub 1 over I sub 2. Remember, those I's mean intensity. Okay, and then finally we can use this new skill we have of changing from log form to exponential form to help us isolate I sub 1 over I sub 2. So log base 10 of I sub 1 over I sub 2 equals 1. To change that to exponential form, here is our base, and here is our exponent. So we will have 10 to the first equals I sub 1 over I sub 2. And if we think about moving that I sub 2 over, it means that I sub 1, the intensity of the first earthquake, the 7.9 on the Richter scale, is equal to 10 times I sub 2. Which means an earthquake of magnitude 7.9 is 10 times as intense as an earthquake of magnitude 6.9. So it's kind of an interesting comparison. All right, so that does it. Hopefully that helps with some of the homework problems if you need it. And we will move on to 7.4 tomorrow. Your homework for this section was page 456. I'll write this down back here. Page 456, 15 through 75, every other odd. So again, that was page 456, 15 through 75, every other odd. See you in class.